I have the privilege of calling your attention today to what is probably one of the most far-reaching generalizations of the human mind. And while we're admiring the human mind, which is something we enjoy doing, it's always somebody else's human mind that we enjoy admiring. We should take some time off to stand in awe of nature, of a nature which can follow with such completeness and generality such an elegantly simple principle as the law of gravitation. And what is this law of gravitation? It is that every object in the universe attracts every other with a force proportional to the mass of each and varying inversely as the square of the distance between them. If you like mathematics, you can write that same thing as an equation, proportional to the mass of each and inversely as the square of the distance between them times some constant. Now, if I add to this the fact that an object responds to a force by accelerating in a direction of the force to a degree inversely proportional to the mass of the object, I will have said everything. And were you sufficiently talented mathematicians, then you could figure out all the consequences of this. But Tycho Brahe had an idea which was different than anything that the Greeks had, and which is following: that these debates about the motions and the meaning of the motions of the planets could best be resolved if we would measure where they really were sufficiently accurately. That if we knew exactly how they moved by measurement, then maybe we could decide against one or another viewpoint. This is a tremendous idea, that you should do some careful experiments instead of deep philosophical arguments and find something out. So, as a result of this, for many years he studied in his observatory on an island the positions of the planets and made great tables, which were then studied by the mathematician Kepler. And he discovered from the data that there were some very remarkable, beautiful, and simple laws that the planets obeyed. The planets do not go around at a uniform speed, but when they're nearer the sun, they move faster, and when they're further from the sun, slower. In what way? In precisely this way: that if you look at the planet at two successive times, let's say a week apart, and draw the two lines from the sun, it encloses a certain area. If you did it at another part of the orbit here, where it's further away, the area enclosed in the same length of time, day a week, would be the same. So we say equal areas are swept out by the radius vector in equal times, and that determines the speed around the orbit. That if you compare two planets which have different orbits of different sizes, then measure size by what is technically called the semi-major axis, which is just a half of this distance across here, that the length of time the planet takes to go around it, its complete cycle, varies as a 3/2 power of the semi-major axis. To make it simpler, if the planets went in circles, and they nearly do, then the time it takes to go around would be proportional to the radius of the circle to the 3/2 power.